Today we'll see preposition 2.5a in chapter 3 of our textbook, and let's see how we can prove the same. So for that, you can see what you have to prove as the statement of preposition 2.5 here. It says that suppose we have a function f of z which is equal to summation n is equal to 0 to infinity an into z minus a the whole raised to n, which is having the radius of convergence capital R strictly greater than 0. We have to prove that presently we are proving A. We have to prove that for every k greater than or equal to 1, the series given here, which is equal to summation n is equal to k to infinity, n into n minus 1, etc. n minus k plus 1 into an into z minus a the whole raised to n minus k has the radius of convergence capital R. So we have to prove this theorem. So let's see how we can prove. So first of all, we know that f of z is equal to summation n is equal to 0 to infinity an into z minus a the whole raised to n. This is what we have at hand. So in order to prove the same, what we take is that we assume that a is equal to 0. So this is simply for our easiness to prove. Okay. So the next thing we are going to do is assume we are going to prove the theorem for k is equal to 1. And if we prove this for k is equal to 1, rest follows by induction. Okay. So we have assumed that without loss of generality that a is equal to 0 and we are assuming that k is equal to 1. Okay. So we had earlier seen that suppose if we have a series summation n is equal to 0 to infinity a n z raised to n is given to be convergent. Suppose if it is given to be convergent and the radius of convergence is given to be capital R, okay, for this series, then we had earlier seen that 1 by R is equal to limit supremum n tends to infinity modulus of an the whole raised to 1 by n. So this is 1 by n. Okay. So now we are assuming that k is equal to 1 as we earlier said. Then if k is equal to 1, we have summation n is equal to, there was a k here. So we are substituting, instead of k, we are substituting 1 to infinity. The terms will become n into an into z minus a the whole raised to n minus 1. Okay. So our aim is to prove that summation n is equal to 1 to infinity n into an into z minus a the whole raised to n minus 1 has radius of convergence capital R. This is our A. So that is our aim is to prove that 1 by R is equal to limit supremum n tends to infinity. So instead of an earlier for earlier series, here we have the coefficient to be n into an, which is the coefficient of the term n minus 1. So you should analyze the variation of the coefficient and the power here. Okay, so here that will be modulus of n into an the whole raised to 1 by n minus 1. So this is what we have to prove. Okay. So for that, we are first looking at something called, we have, okay, think about limit n tends to infinity, n raised to 1 divided by n minus 1. You're thinking about this, okay. So now I'm drawing a column here, okay, and I am letting 1 by n minus 1 as an x. Okay, that means n minus 1 is equal to 1 by x, which implies x is equal, n is equal to 1 by x plus 1. Okay, n is equal to 1 by x plus 1. That means when n is tending to infinity, okay, what happens? X is tending to 0, right? So here we are just interchanging our things. So here we have limit, instead of n we are having x tends to 0, okay? And here we have, instead of n I can substitute 1 by x plus 1 the whole raised to x, because we had assumed like that here, right? Okay, now here we had assumed like this. Okay, now it is like this. So now what we are going to do is, this is equal to, I'm going to write something like this, e raised to logarithmic function over e limit x tends to 0 1 by x plus 1 the whole raised to x. Because this is e raised to log means that will be nothing but the index here. This is a property of e raised to log of x is equal to x. Okay. So since this function is continuous, we can interchange this limit and log here. Okay. They are interchangeable here. Exponential function is also continuous. So we have e raised to limit x tends to 0 log of 1 by x plus 1 the whole raised to x. Okay. Now let's see what happens. So we have the limit and log. Okay. So that will be equal to e raised to limit x tends to 0 x into log of 1 by x plus 1 the whole raised to x. Okay. Oh, sorry. The whole raised to x can be cancelled. Okay. Here it is just log of 1 by x plus 1, because the x got down. and this is equal to e raised to limit x tends to 0, okay, x into limit x tends to 0, 1 by, here is a log 1 by x plus 1, just applying limit on the product here, okay. So that is equal to e raised to 0 into limit x tends to 0 log of 1 by x plus 1, which is equal to e raised to 0, which is equal to 1. So now we just said limit of n tends to infinity n raised to 1 by n minus 1 is equal to 1. This is what we proved. Now, okay. Now we have to use this in the as we move on into the proof. Okay. So now you have a question for the day to solve. So this is the assignment for today. So the assignment is nothing but exercise number 2 of the section. It says if an comma bn are positive real numbers, the coefficients, such that we know limit of bn as n tends to infinity is equal to b, okay, that is strictly greater than 0, and limit supremum of n tends to infinity an is equal to a. Suppose we know this, you have to prove that, then prove that limit supremum limit supremum n tends to infinity an into bn is equal to a into b, that is equal to limit supremum of n tends to infinity an into limit n tends to infinity bn. So this is the question for today, and you have to do it as assignment. Okay. Okay. Now that we have uh, the question for the day to be solved by you, we are thinking about something else. Okay. So what we wanted to prove was that 1 by r is equal to limit supremum n tends to infinity modulus of n into an the whole raised to 1 by n minus 1. This we have to prove. Okay. So now you are thinking about this session. Okay. The session sitting here. Okay. So think about limit supremum n tends to infinity modulus of n into a n the whole raised to 1 by n minus 1 is equal to limit supremum n tends to infinity, okay, modulus of n raised to 1 by n minus 1 into modulus of a n raised to 1 by n minus 1. Okay, this is equal to limit supremum of n is a natural number, so it is positive 1 by n minus 1 into limit supremum, the product of limits that works here also, into 1 by n minus 1. Okay, here n tends to infinity. Here also n is tending to infinity, which is equal to limit supremum. If the limit exists, the limit and limit supremum are the same. So you have like this, right? Supremum of n tends to infinity, modulus of an the whole raised to 1 by n minus 1. Okay. Now we had proved that the value of limit n tends to infinity n raised to 1 by n minus 1 is equal to 1 into limit n tends to infinity, sorry, limit supremum n tends to infinity, modulus of an the whole raised to 1 minus 1 by n minus 1, right? Which is equal to limit supremum n tends to infinity, modulus of an the whole raised to 1 by n minus 1. So what we now proved is very useful as we move along this proof. We just proved that limit supremum n tends to infinity, modulus of n into an the whole raised to 1 by n minus 1 is equal to limit supremum n tends to infinity, modulus of an the whole raised to 1 by n minus 1. Okay. So now it suffices to prove that 1 by r is equal to limit supremum. We had to prove that 1 by r is 1 by r is equal to limit supremum n tends to infinity, modulus of n into n the whole raised to 1 by n minus 1. Okay. Now what did we prove? We proved that that is equal to what, right? We just have to prove 1 by r is equal to limit supremum n tends to infinity, modulus of a n the whole raised to 1 by n minus 1. Okay. Now we are thinking about something else. Okay. We are thinking about the series. Consider summation n is equal to 1 to infinity an into z raised to n minus 1. Okay. And since we know in the hypothesis that, right, in the hypothesis we had uh, summation n is equal to 0 to infinity an into z minus a the whole raised to n have the radius of convergence as r. That means summation n is equal to 1 to infinity a n z raised to n is convergent. So that means summation n is equal to 1 to infinity a n. There is just a small difference. When earlier it was a n into z raised to n, here it is just a n into z raised to n minus 1. Both are the kind of similar series. So this series also converges, but the radius of convergence will have a change. So we are assuming that this series has the radius of convergence to be a number r dash which is strictly greater than 0. Okay. Since this r dash is the radius of convergence of the series we just considered now, we know by the definition of radius of convergence 1 by r dash is equal to limit suprema n tends to infinity. Here we have the coefficient as modulus of an and the power as 1 by n minus 1. Okay. Now we know that. And we are now rewriting the same series. Summation n is equal to 1 to infinity a z raised to n minus 1. Okay. This series can be written like this, right? Summation n is equal to. Okay. Here it starts from a1 plus a2 Z plus A3 Z square like that, right? So here I am writing n is equal to 0, okay? 0 to infinity. Then you have to write, instead of an, we have to write an plus 1, okay? Here it will be z raised to n, right? Both are same, right? Okay. And now we are going to write the series we have at hand. Okay. Summation n is equal to 0 to infinity. An z raised to n. Okay. This is equal to a naught plus a1z plus a2z square plus a3z cube plus etc. Right? Okay. That is equal to a naught plus z into a1 plus a2z a2z plus a3z square. Like that we can take the z out of here, right? Okay. Now this is equal to a naught plus z into, the series here can be changed into n is equal to 1 to infinity a n z raised to n minus 1, right? So this can be written like this. Yes. And that is nothing but we just had rewritten that series to be summation n is equal to 0 to infinity a n plus 1 into z raised to n. Okay. So presently we are having, presently we are having, sorry, presently we are having hmm, r dash to be the radius of convergence of summation n is equal to 1 to infinity an z raised to n minus 1, which is equal to summation n is equal to 0 to infinity. It could be written like this, right? So we are just rewinding that. Okay, we are having this. Now, if modulus of z is strictly less than r dash. Okay, now we are thinking about modulus of summation n is equal to 0 to infinity an into z raised to n. Okay. This is equal to modulus of a naught plus z into summation n is equal to 0 to infinity a n plus 1 into z raised to n, right? Can we write like this? Yes, we just said that earlier. Okay, we said that earlier. Okay. So that is less than or equal to, by the triangle inequality of the modulus function, we can write that as less than or equal to modulus of a naught plus modulus of z, because the modulus function acts on product like this, modulus of z into modulus of summation n is equal to 0 to infinity a n plus 1 into z raised to n. Okay, that is less than or equal to modulus of a naught plus modulus of z into, again we are applying the triangle inequality here, summation n is equal to 0 to infinity modulus of a n plus 1 into modulus of z the whole raised to n. Okay, So that's how we just rearranged. Okay. Suppose I think here we can even just remove that and write like this. Just simply um, a n plus 1 into z raised to n modulus. Okay. We are just writing else. Now, we assumed this a naught is simply a complex number. Okay. And this modulus of z we had assumed that is strictly less than r, right? R dash. So here I can have an strict inequality, and I am writing modulus of a naught here. Plus here we have r dash. Okay, and think of this series. We just said that this series is having, yes, the same value, no, the same radius of convergence without this modulus function. See, we just saw that r dash is the radius of convergence of summation n is equal to 0 to infinity a n plus 1 into z raised to n. Okay, so this was the radius of convergence of this series. But here the series is having a modulus function here. Okay, so when we are thinking about the modulus function, we have to remember that when we were progressing through the proof, we had assumed that all the ans are positive. It was a question for the day which you have to prove. Okay, all the we have as we progress, we assume that all the uh, coefficients were strictly greater than zero. Okay, so we can say that this modulus summation n is equal to 1 to infinity, this modulus will work as the same series summation n is equal to 0 to infinity a n plus 1 z raised to n. That means this series is also a convergent series, and it converges to some uh, number capital M, say. So all these are finite quantities, so we can say that this is strictly less than infinity. Okay, so see the series. This was a series which we said in the hypothesis at first. Summation n is equal to 0 to infinity a n z raised to n has the radius of convergence capital R. That was what we assumed. Now we assume that modulus of R is strictly modulus of z is strictly less than r dash, and then also the modulus of the series was strictly less than infinity. But the radius of convergence of the series is capital R, which is the largest possible such capital R. That means here we can say that this r dash is less than or equal to capital R. This is what we got now. Okay. So our next aim is to prove that capital R is less than or equal to capital R dash. Let's see how we will prove that. Okay. So now we are assuming that if modulus of Z is strictly less than R, and suppose if Z is equal to 0, then what happens? Then summation n is equal to 0 to infinity a n z raised to n is nothing but 0. Okay, we have nothing to prove there. Okay, if it is so, the series is convergent. Okay, so in the next session, we are saying if modulus of z is strictly less than r and this z is not equal to 0. I'm assuming like that. Okay. Okay, assume we know that in the hypothesis, what did we say? Summation n is equal to 0 to infinity. A and z raised to n has the radius of convergence as capital R. This we know them. Okay. Now, when modulus of z is strictly less than r means summation n is equal to 0 to infinity a n into z raised to n will have a finite sum. Okay. And since these ANs are positive, this is equal to summation n is equal to 0 to infinity modulus of an set raised to n, and since this is strictly less than infinity, this will be also strictly less than infinity. Okay, now let's see how to progress. We have summation n is equal to 0 to infinity an set raised to n. Okay, that to be less than or equal to modulus of a naught plus modulus of z into summation n is equal to 0 to infinity modulus of a n plus 1 into z raised to n. We just proved this before. Okay, now summation n is equal to 0 to infinity modulus of a n plus 1 into z raised to n is equal to modulus of, we are just expanding the terms. This is equal to modulus of a1 plus modulus of a2 into z plus modulus of a3 into z square plus modulus of a4 into z raised to 3 plus etc. Okay, that is equal to, and just dividing and multiplying by mod z. Okay, the same terms, modulus of a1 plus modulus of a2 into z plus modulus of a3 into z square plus etc. Okay, now this is equal to 1 by mod z. Okay, and when I am multiplying this modulus of z into this braces, I am going to get modulus of a1 into z plus modulus of a2 into z square plus modulus of a3 into z cube plus etc. Okay, now I am going to add a modulus of a naught and subtract a modulus of a naught. Okay, so this is equal to 1 by mod z into all this series together is modulus of a naught plus modulus of a1z plus modulus of a2z square plus etc. And then minus a naught, minus modulus of a naught. So we can write here as okay, as summation n is equal to 0 to infinity modulus of an into z raised to n. Okay, minus modulus of a naught. Okay, that is equal to 1 by mod z into summation n is equal to 0 to infinity modulus of an into z raised to n minus 1 by mod z into modulus of a naught. Okay, so since z is not equal to 0 in this case, 1 by mod z will never become a large quantity, and as we already said, this value will be a finite quantity and this a naught is a definite complex number. So the difference here is strictly less than infinity. Okay, and you know that the radius of convergence of this series is r dash. Okay, and we had assumed all these in modulus of z strictly less than r. But the radius of convergence is the largest possible real number in which the convergence happens. So in this case, we just prove that r is less than or equal to r dash. Thus, what we proved is r is equal to r dash. So what was R dash? What was R dash? R dash was limit supremum modulus of a n the whole raised to 1 by n minus 1. N tends to infinity. So this was the, we had earlier said that we had to prove capital R and the term sitting in the right are the same. So what we now proved is this. So note that we had assumed that uh, a is equal to 0 and also k is equal to 1. Okay, and by an inductive argument we can say that this happens for every k greater than or equal to 0, and this is how we prove the preposition 2.5a. And so that is all for today. Have a great time and let's see soon. And thank you.